It's my turn to introduce one of our stars, Ryan Rodgers. Ryan is at the National High Magnetic Field Laboratory Ion Cyclotron Resonance Facility at Florida State University. I had to read that, it's a mouthful. I suspect that some people in this room are not highly technical spectroscopists. So just a few words of background. This morning we heard a nice talk from John Farrington who went through some of the history of this. And John, I sat through all those seminars. And we were treated to gas chromatograms where there's a few peaks and a big lump in the middle that was unresolved brown matter. We then moved on to mass spectroscopy, and I found these talks, if anything, a bit less convincing. They would pick away at this stuff but not really tell you what it was. And then we had GoMRI, and Brian showed up. And all I can tell you is when I first heard that talk, it felt the moment in the Bible when on the road to Damascus, Saul becomes Paul, and the scales fall from your eyes, and you think, oh my God, that's what this stuff is really like. It was amazing. What Ryan does is take this enormously complicated stuff called oil and break it apart into its component parts. But he's not satisfied there. The oil becomes weathered. It's attacked by oxygen, it's attacked by light, by photons. It breaks down into even nastier pieces. And all this can now be seen with the techniques built here. Going further than that, you go blind looking at the blizzard of data, and in the words of one of Ryan's own papers, he finds islands and archipelagos in a sea of data. And he's here to tell us about what oil really looks like. Ryan grew up in the Florida Panhandle. He's not moved too far from home, and for that we are fortunate. Ryan, the floor is yours.
Thank you for the kind introduction. So hopefully I'm going to take you on a molecular level journey on diving into the complexity of oil and what happens to it during the spill. Specifically, the first thing that happens to it is it falls in the hands of people like this. This is a group that comprises researchers from Hui, Bigelow, and also the National High Magnetic Field Laboratory. These are the people that really get the stuff done. Chris Hendrickson and I were talking about old school, in the light of the death of Kobe Bryant, we're talking about old school Michael Jordan games, and being involved with this crew reminds me of one of the funniest quotes I ever heard was Michael Jordan came back from retirement and hung 55 points on the New York Knicks at Madison Square Gardens. And Bill Wennington is a, travel center, pretty much didn't amount to too much in the NBA. But when he was interviewed afterwards, he says, I'll always remember tonight as the night that that Michael and I combined for 57 points to beat the Knicks. Bill had 2 points. Michael Jordan had 55. So when you're part of this group, sometimes you feel like Michael Jordan and sometimes you feel like Bill Wennington, and that's okay. So we were charged with understanding this progression from, of course, the deep water release, flow up to the surface, you get surface slicks, and then by some magic, you get these thick emulsified mats, commonly referred to as mousses, which can find their way inshore and tumble in the surf and become tar balls. And the question is what the heck is going on here? Specifically, it's what is this? How did it form? How am I going to analyze it? And how am I going to leave legacy methods behind so that these can be used in future spills to understand what's going on? And so what we do, of course, is go to the literature, and as scientists, we stand on the shoulders of giants all the time. And so we went to the Ixtoc spill, and we have John Farrington and Ed Overton, and they put forth, these 3 fundamental reactions that they feel occurs in photochemistry. But they note that this is a real pain because analytical instrumentation at the time just wasn't able to deal with oxidized species because of their increased boiling point and their thermolability. So when you start sticking carboxylic acids on petroleum and you stick it in a hot injector in a GC port, CO2 is this marvelous leaving group that just comes flying off, and then you lose the information that you're looking for. And so they openly say, we need advanced techniques to start looking at these problems. And then you get Thingstad and Pingerud, who, geniuses, just put forth this paper on the formation of chocolate mousse. This is 83, so this is after the Farrington and Overton paper. And they just straight out, I've read the paper, with very little evidence, they just come out firing and they say, you know, it's suggested that photochemical oxidation of oil components leads to the formation of surface active, so these are surfactants, oil-soluble surfactants, and these partition to the oil-water interface and start to take up water. And they just throw it out there. This must be happening. But there's very little molecular evidence for how this happens, the products, and the timescales over which this occurs. And so this is a real analytical challenge, because GCMS, if you look at the native hydrocarbons in the petroleum, depending on the petroleum, you can only see about half of the material that's there. The other half doesn't go through the GC column. And then when you oxidize it, the boiling point goes way up and it becomes thermally labile, and you can get polyoxygenation, which can create surfactants. So you have to have a technique that can handle all of this complexity, on top of the fact that Overton and Farrington said that you can have photopolymerization, so two hydrocarbons come together. Now this is twice the mass of this, more than twice the boiling point, then you start oxidizing it, it goes nuts really quick. And then you can also have a large hydrocarbon molecule that cracks into two pieces, and these pieces start oxidizing. And so the chemical complexity of the starting material alone challenges any analytical technique in the world. And now you're talking about, you know, letting loose all these different reactions to create products. So it was a real challenge. But luckily, at the National High Magnetic Field Laboratory, we have the highest mass resolving power mass spectrometers in the world. And so this is the highest field FTICR in the world. Its brother and sister are sitting right here in the next room, which are number 2 and number 3 in the world as far as performance. And so if there's any mass spectrometer on the planet that can handle this complexity, it's the mass spectrometers at the Magnet Lab. And so what complexity am I talking about? This is a VAC residue from a petroleum sample. This is a single mass spectrum, and there's 106,000 different peaks that are in that distribution. And none of them will go through a GC column. And this is before we started oxidizing anything. And so the complexity is pretty spectacular. And just to beat a dead horse, if you zoom in at one spot in that mass spectrum, there's 462 peaks at one nominal mass. So 462 peaks would be good in a normal mass spectrum. But this is 462 peaks at a single nominal mass. And you've got 1,000 nominal masses in there. So the complexity is pretty insane. And if you zoom in even more, here's a quadruplet, and the mass difference between each one of these peaks in the quadruplet is at or less than the mass of an electron. And so the mass of an electron. And so these are the mass differences that you have to resolve and identify the elemental composition by accurate mass. And with accurate mass, we're talking about you have to resolve all of these things and determine the centroid of that peak in 50 part per billion accuracy in order to do this. But it does work, and when it works, you take the mass spectrum, you take the accurate mass of all the peaks, you feed it into a computer program that we write, and it gives you the elemental composition. And so this is the magic of the technique. You weigh something, and you get the elemental composition. It's sort of like building a castle out of 5 different Legos, and then weighing the castle, and you can tell how many of each Legos was used to make it, except the Legos are the periodic chart, right? So this is the magic. So we weigh something and we get the elemental composition. From petroleum science, we know that from that elemental composition, you can determine how aromatic it is. So as you go up in DBE, or double bond equivalence, you get more aromatic. This is the number of rings plus double bonds. Benzene is 4, because it has 3 double bonds and 1 ring. And so anything above 4 can be aromatic. And then the heteroatom class. So this thing contains nothing but hydrogen and carbon except for 1 sulfur, and so we group them all into the S1 class. Now, you're going to see a lot of these, and it's the only one I present, because I promised Chuck I would go sparingly on the mass spec lingo. But if this thing starts oxidizing, then the S1 class will go to SO, SO2, SO3, SO4. And so all of these species will start increasing in heteroatom content in the addition of oxygen. So we go back, and so we say, okay, we've got $20 million worth of mass spectrometers. We're ready to go. The problem is that this boiling point issue with the OX species was still an issue. And it was an issue until John Finn. He won the Nobel Prize in 2002. The name of his Nobel laureate speech was Electrospray Wings for Molecular Elephants. In other words, making elephants fly. So nowadays, I know this is mind-bending, but you can launch the ribosome into the gas phase, right? So the vapor pressure of the ribosome is 0, but you can launch it into the gas phase, gigadalton type things. You can launch whole viruses into the gas phase, all based on this technique. So voila, there goes the boiling point restriction. So when we started looking at the first samples that were coming in, we of course did high-end GC-GC analysis, and this stuff is fantastic. And so this, Chris Reddy calls this bookkeeping, right? Because you resolve and identify a lot of times down to the isomeric level of everything that was spilled into the environment, and then you can watch how it changes. So you're bookkeeping, you're seeing how these disappear, and you can see evaporative loss, water washing, and all sorts of fantastic things. And so that's why we collaborated with Hui on this side of it. But they also did some bulk measurements that showed that if you did thin layer chromatography, that this polar peak goes through the roof, right? As it oxidizes in the environment, oxygen goes up, and it goes up at the expense of saturates and aromatics. And I'll get into that a little bit later because that was pretty controversial at the time. And so they're seeing oxygen go up, but they can't identify any of it in the GC-GC because of the restrictions that I've already discussed. So then we get in, this is literally the first sample we ever looked at. This is from Pensacola Beach. And so we identify the Macondo well oil is here, 13,000 peaks, and then we identify what was in the environment. And now we're not looking at what went away, which is what GC-GC was doing. We got almost triple the number of peaks. So something's going on, right? Something is increasing the complexity of these materials in the environment. And so if we zoom in at one nominal mass and we compare these two, and I'll flip this guy upside down, then here is what we found in the environment, here is what was spilled in the environment. Everything that has red is oxidized. And so you have a massive oxidation process going on in this material in the environment. And the consequence of that is as oxygen amount increases, they start self-associating more, they form skins and films and other things that can encapsulate material, and you end up getting tar balls. But that's fast forwarding a little bit, so we'll start from here right now. And so the other cool thing is that we identified in negative ion mode, you can deprotonate and make acids. Well, they require 2 oxygens because it's a carboxylic acid, so you see a huge onset at 2 oxygens. So here are all your acidic things that are formed, and here are all your things that contain ketones. And this took a little bit of figuring to do, but we got this all worked out, that these are ketones and these are acids. And so now you're looking at the chemical functionality specific information of oxidized products in the environment. So you're taking it from just identifying it to identifying the chemical functionality. And this is going on all over the place. So Juan Chen, who will be presenting on Wednesday, will summarize an 8-year study in the Barataria Bay region and understanding how these things change as a function of time. But the source of this was still debated. I mean, Atlas a long time ago said that, and Jim Payne and others have pointed out that the biodegradation that occurs in surface slicks is relatively low, suspected to be low because of nutrient limitations. So we suspected that this was due to photooxidation, but we had to do our due diligence. And so fast forward, I'll just give you the punchline. All of our biodegradation microcosm studies produce water-soluble species only. So everything that we were looking at in tar balls and other things were oil-soluble. So we were looking at things that produce oil-soluble, but bio-ox and biodegradation does not. It only produces water-solubles. So that's off the list. But Phoebe pointed out, who was working in our lab at the time, that photo-ox generates a ton of oil-soluble OX species. And so you get these single oxygen, double, triple, all the way to 10, 11, 12 oil-soluble species. And it turns out that they match Juan's field data very well. And so now we're starting to get confidence that, that this is due to photooxidation. And we take it one step further because now we have the elemental composition of everything. Here's what we identified in the salt marsh and the acids. Here's what we reproduced in the photoox microcosms. They match almost perfectly. I told the graduate student, I'm like, you almost can't make up data that's that good, right? Especially when you're dealing with complex systems like this. So then we took it one step further and say, okay, those are the acids, but we can do ketones as well. Here's the ketones. Here's irradiated in the lab, and here's identified in 3 different field samples. Again, the match is almost too good to be true. So this is all pointing that photoox is what's producing these oil-soluble species. Sydney's going to present on Wednesday as well, and she did the ketone work, that we're now taking it down to given sulfur chemistries, either sulfides or thiophenes, and you can actually see differences in the water solubles and oil soluble that they produce. So again, taking it all the way down to individual functionalities that are known to exist in petroleum. So then we get to Thingstad's hypothesis, that these things produce surfactants, and this is what causes the swelling with water in these mousses, as he termed them. And so we did some photoox. So Matt Tarr is another collaborator who's been a huge part of this research, and Phoebe showed that you can generate peanut butter, is what we called it, from photoox of surrogate. If you really mix it, you overmix it, you can end up getting these peanut butters. So that was pretty indirect evidence, but the question was what species were doing this? And so if we go back, we already showed that, Thingstad said that they were oil soluble. Well, we already identified oil soluble species in photoox. So now we're presented with another question, is that of these oil solubles, are any of them interfacially active? And so it just so happened that we had a method to generate interfacial material. And it was due to petroleum work, it wasn't due to this work. So we very happily walked over to the petroleum research side of ours, grabbed that method, and walked over to the environmental side and said, well, we can easily address this problem. And so when we took the oil solubles and we separated them on this column that separated into interfacially active and interfacially inactive, then this distribution split. And it split into oil-soluble inactive, oil-soluble interfacially active, and then water solubles. And so this peeled everything apart. And so you can see that the behavior of these molecules is dictated by their oxygen content. If you have low oxygen content, then you're going to remain oil soluble and you don't want anything to do with water. If you become polyoxygenated, then you start to interact with water. If you get too oxygenated, then you really like water and you end up leaving the oil and going in as photosolubilized carbon, all dictated by oxygen number. But, as an analytical chemist, this bothers me because there are huge overlaps in these, pseudo-Gaussian distributions. So why in the heck is 104 not interfacially active and the other that has 4 oxygens interfacially active? And so we did a second experiment that showed that the reason that is because of carbon number, which makes sense. If you're very high carbon number, you can have very high oxygen content because the number of oxygens per unit carbon is still low. Then you don't become interfacially active. But if you have, as you increase the amount of oxygen, if you have low carbon number species, then they start to partition to the oil-water interface. And then if you add even more oxygen, way up here, then you become water soluble. It also showed us that it doesn't matter how many oxygens you throw on something, it's not going to go in the water, right? So you get this huge exclusion zone of 30 carbons and higher that, it takes 22 to 20 oxygens per molecule to get something that high a carbon number into the water. And so everything is starting to make sense. And we also took field samples and we fractionated them the same way, and we get the exact same answer of these surfactants that are present in weathered samples. And so this tells us that photooxidation is the reason that they're there. So here's the diagram that we have. In the dark, oil goes into the environment. Naturally occurring surfactants will partition to the oil-water interface, but as you start to irradiate it, then you're oxidizing from the oil that becomes interfacially active. You then oxidize from the interfacial material into water, and this continues until you're getting hundreds of ppm of DOC being driven into the seawater. So it is a major contributor to DOC. So we've got all these alcohols, sulfur-containing ketones, aldehydes, and ketones and acids. We've got those under control. And so now in the last 5 minutes, I'll get back to the main thing, and this was the structure dependence. So now we're going all the way through elemental compositions, through chemical functionality, and now we're going to individual structural motifs. And so Marta, who was a postdoc in our lab, we're not dumb. We just hired her as a staff member because she's done fantastic work. She'll be talking about this Wednesday at 3 o'clock. So we get back to Farrington and Overton's conclusions from Ixtoc that photooxidation, and this is a huge, I was surprised it stuck their neck out like this. So they're saying that photooxidation occurs on aliphatic and aromatic compounds. Why is that significant? Because aliphatic compounds don't have a chromophore. And so they can't absorb light and undergo what's called direct photooxidation. They need a buddy, right? They need someone else to absorb the light, then activate them, and then oxidize. So this, I was surprised, but it's in print. They said it. It's aliphatic and aromatic. And so when we address this is pretty simple because Sydney and Marta and even Phoebe had torn up these microcosms and field samples, looked at ketones and acids and everything else. So it only takes one slide to show that this is true, and that's this one, right? So anything under DBE5 has to be aliphatic, and there are a ton of aliphatic oxidation products. So check, they were right. And of course the aromatics are above them, so this whole compositional space is a fingerprint, or the photoox fingerprint of that crude. So then we go to this one, polymerization, and so this is, you're going to take two individual molecules and they're going to photopolymerize into something that's bigger. Well, as a petroleum scientist, the easiest way to do that is start from a boiling point. So you start from a boiling cut, then you restrict the carbon number to a very narrow space. And so then we're going to photoirradiate this, but we know the DBE and the carbon number range of the starting material, and that's this green region. And then we look at the oxidized products, and there's thousands of them. I'll just give you a snapshot. There's the O10. So you're double the carbon number, double the aromaticity. So there's nothing in there that has that carbon number. So the only way it can form is by photopolymerization. So check, we got that one as well. The next one is photodecomposition. For that one, we have to go to asphaltenes, which are very controversial in petroleum science and just woefully dealt with in environmental science. So much so that we're trying to figure out new names for them because the things that you isolate from environmental samples are not asphaltenes. Don't call them asphaltenes. So these are the native asphaltenes from petroleum. We stuck those on a film and we irradiated it, and here's the carbon number distribution of the starting material, and already we're getting oil-soluble crack products. But the question is do these end up going to water? And so the question is do any of these crack products start showing up in the water? And again, I'll spare you with literally hundreds of thousands of molecular formula and just show you, yes. So here are the ones that contain 3 oxygens. And when you compare them to the O3s that are oil soluble, you see the exact same carbon number dependence that I pointed out before. They sit right to the left at lower carbon number to the O3 oil solubles. And so this is all making sense. So when I said it was complex, it's complex. So this is the heteroatom class distribution of the asphalt. And so you have your sulfur and then all of your SOXs. And then you have your hydrocarbons and all of the OXs. And then you have your S2s and all of the S2OXs. And this is just half of it. So just indulge me. Here it goes for the nitrogen containing, the nitrogen sulfur containing. All of these are being oxidized and driven to the water. So in all, there's 82 different heteroatom classes. In each one of those heteroatom classes, there are thousands of individual members. And so you're literally talking about hundreds of thousands of different water-soluble and oil-soluble species being identified. So I'll end with this, is that if you thought asphaltenes were insane, they're even more insane because there's a structural motif that was thought not to exist that Marta in our group just proved did exist. And so if you took the conventional wisdom of what an asphaltene is, that's this molecule. And she's actually got a way to separate the different structural motifs. So if you take this motif, which is called an island because it only has one aromatic core, and everyone says that this is what asphaltenes are. If you irradiate that, you get black tar at the bottom and clean water, right? These are the water solubles that are in there. There's like 50 things. If you take the structural motif of an asphaltene that was thought not to exist, but Marta can magically isolate, this is what you get. Now, I don't know about you, but I'd rather drink that water than that water, right? So this is the archipelago structure and is shown to generate on the order of 15,000 different water-soluble oxidized species. And so not only does chemistry matter, structure matters, carbon number matters, it all matters on determining where it goes. So with that, these are the summaries, and of course I'll make this presentation available. I don't need to read through all of them, but basically it's photooxidation is very important. It creates surfactants, they swell, they create the gelatinous mousse, they further oxidize, self-associate to produce skins that ultimately yield to tar balls that wash ashore. These interfacially active species create an oil-water interface, but we don't know the importance of that. Is that dictating the amount of material that can partition from the oil to the water because it has this interfacial material in between it? That is yet to be determined. So with that, I know GoMRI funding is winding down, and like I said, there's $20 million of mass spectrometers. NSF does not expect you to have that in your lab. That's why they put it in our lab. So we're an international user facility. We provide mass spec services, high-resolution mass spec services free of charge. And so if you're interested, I'll be here all week, and Marta and Sydney and Juan will be here as well. Thank you for your attention.
Wow, well, thank you. We don't have any written questions handed in. I thought there's not a huge number of molecular spectroscopists in the audience. I do remember the moment on the research board when we first looked at a pile of proposals and we had to vote on whether to include a photochemistry program, and I'm so glad we did. This material might be hard for the outreach panel to communicate. So I've got one question for you. If I look at the difference between, say, this event and the Exxon Valdez event, which John Fountain talked about this morning, a lower temperature and less photoactive environment, lower light levels. Is there any way that you can think, we could start to scale the difference between the two to give a little bit more predictive value as to the fate of oil in different light regimes?
Yes, so we have started doing that. So as part of the GoMRI funding, we knew that looking at Macondo well oil and its surrogate would not fly. So we've done a heavy fuel oil, we've done a residual fuel oil. We've also looked at Athabasca bitumen in the occurrence of potentially a loss of dilbit or other materials that are constantly being transported in the world today. We do see profound differences, and the reason that we're teasing apart the chemistry and structure is to try to understand where those differences are coming from. Is it only a mass distribution of heavier molecular weights versus lighter molecular weights? Or is it that a lot of these heavier materials have high sulfur content, high thiophene content, high sulfide content? Could those be driving other chemistries? And so, if Grid C is here, they're probably, I've got a dot on my head. They're ready to take me out because, I've got so much data that I have to upload to them. I'll be dodging like this, but so we do have all that data. We're pouring through it right now, and in the synthesis document on the analytical side, we're hoping to have something to say about that. Yes.
One very nice question from the audience. How does the addition of oil dispersants to the system affect the photooxidation processes?
Yeah, so we have looked into that. It increases the penetration depth of the sunlight is relatively small. So if you disperse across the surface and increase surface area, you're going to get enhanced photooxidation. The problem is that the application window is narrow with aerial dispersants, and the reason that data that's not being presented yet is that the reason that dispersants start to fail on this photoox crude oil is because they have their own surfactants in them. So their in situ generation of surfactants from sunlight have already pre-treated the oil with given it's a crappy dispersant because it's just blind oxidation of, the hydrocarbons are there, but it is a dispersant. And so the reduced effectiveness, so in the early time points, it's good. In the later time points, the effectiveness is going to go way down because it has surfactants already present. And so we've started to work with Nalco on the idea of that at later age films, that they should be using emulsion breakers in combination with dispersants, because they have these chemicals. I know because I work on the oil side, is that so things that have already swollen with water, they could treat with emulsion breakers to break that down, and then dispersants to break that up. So we're still working on ways that we can do that as well.
Just one very quick question. Different wavelengths of light, what are the critical wavelengths?
Aha. So Colin Ward is the photo-ox guru, and I can tell you that he is actively working to determine that right now. So that's another part of the GoMRI research, is that all of these connections between Bigelow, Huey, and even Dave Valentine out on the West Coast have now been cemented. So all these projects I'm looking at, wavelength dependence and all sorts of other dependence, they have an analytical solution that is the right price, which is free.
Thank you, Ryan.
Yeah.
Thank you. Time's up.
Thank you.